Kindly start the proceedings. Akshay, start the proceedings of the event. Yeah.
Yes. Good afternoon, everyone. My name is Akshay Ratan, pursuing a master's degree at IIIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of the IAStructE Hyderabad Student Chapter, I want to take this opportunity to welcome our guest speaker, faculty, scholars, the research fraternity, industrial professionals, and all the students to join the online session on the topic Lessons Learned, Risk Mitigation Strategies for the Future. It is my privilege to introduce our guest speaker, Dr. Hemant Kaushik, BIS Chair Professor in the Department of Civil Engineering and the Center for Disaster Management and Research at IIT Guwahati, where he also serves as Dean of Online Education and Skilling. Dr. Kaushik is a well known structural engineer with skills and experience in earthquake resistant design, seismic retrofitting, nonlinear structural behavior, vernacular housing, and earthquake damage assessment. He has led several landmark studies on seismic vulnerability and risk of various building types. He works with BIS technical committees and he is a fellow of the Institution of Engineers and a member of several national and international professional societies. In recognition of his contribution to structural and earthquake engineering, he received the INAE Young Engineer Award in 2010 and was later named as INAE Young Associate. We are truly privileged to have him with us today. Before we start, a small announcement to the participants. If you have any questions or clarifications during the session, please type them in the chat box. We will address them in the Q&A section at the end. Moderated by Dr. P. Praveen Kumar Venkat Rao, Faculty Advisor of the Student Chapter. Now, without any further delay, we will turn the time over to our speaker. Sir, over to you.
Thank you, Akshay.
Thank you, Akshay. And thank you, Praveen, for inviting me to deliver this lecture. So today what I'm going to do is comparing some of the very common Indian building typologies that are constructed in India and understanding the way these building typologies have performed in the past and how we can improve that performance. Not only that, we will also compare the similar building typologies, how they have done in the past earthquakes in other countries. So what I wanted to highlight is that the problem of India is not the Indian problem alone. Many other countries in the world that have similar construction practice are also facing similar kind of problems. So we will try to see how buildings have behaved during past earthquakes. We'll try to simulate that behavior in laboratory by doing very detailed testing on a few building typologies, common building typologies, and then discussing how we can improve that for risk mitigation for the future. Now, I'll go through some of these slides that cover the damage sustained by different types of buildings in major earthquakes during last 25 years. I'll cover some of these earthquakes, not all. That is because I want to concentrate on a few building typologies which are relevant to us. Not those building typologies which are not commonly constructed in India. So therefore, I'll show you some of these earthquakes last 25 years alone. And why 25 years? Because we have seen a very rapid growth of urbanization, very rapid construction growth in our country in last 25 years. Moreover, large number of our design codes are also modified in last 25 years. So what has been the practice in the not only in India but the entire world? How buildings have performed in last 25 years and what we can do to improve the behavior. I'll start with this very big earthquake in Turkey in 1999, that is Kocaeli earthquake, magnitude 7.6. And you can see how these buildings have performed. Now, these types of photographs are common to us. We have seen after almost every earthquake such behavior of these reinforced concrete buildings. But the question is why these buildings are behaving like this, the way they are, the way it is visible in the photographs. So both these buildings are reinforced concrete frame structures, and you can see there are infill walls of different types. So on the left photograph, you can see these are all clay brick infill walls, but on the right side, these are lightweight partitions. So irrespective of the infill type of infill wall, you can see the behavior is poor. The buildings have collapsed. There's no way people can stay here, and I'm not sure how many people would have died during these earthquakes. Both belong to the Turkey. Then the same year, there was another very big earthquake in Taiwan, 7.7, where not only the buildings, but also some other infrastructure like the dam that is shown here in this photograph was damaged, which is quite unexpected. On the right side, you can see what has happened to this building. It's a multi-story apartment building, I think 15, 16 story. The entire building has collapsed during this 1999 earthquake of the Taiwan. And the reason for this collapse may be structural, or maybe due to geotechnical, maybe due to the liquefaction. So when a building collapses, there's a investigation where different people come together. They try to assess the damage. They try to assess the reasons why this is collapsed. And most of the times we find that there's not a single reason because of which such huge structures collapse. There are multiple combination of the reasons, which I'm not sure what was the exact reason for this failure, but you can see how the entire building got separated. You can see these reinforcement bars and these shear walls and these columns, how these are completely separated from the foundation. Then our own Bhuj earthquake of 2001. This was an eye-opener for India because until that time, very few major earthquakes occurred in the urban areas, but this earthquake, which occurred very near to Ahmedabad, and after this earthquake, there were large number of buildings in Ahmedabad that collapsed. And most of these buildings which collapsed in Ahmedabad were residential apartment buildings with open ground story. So after this earthquake, a lot of change happened in India. Where there were many programs that started after this earthquake that resulted in improved construction technology, improved design codes, improved manpower, training of manpower, setting up of state disaster management authorities, although there were some before that. But now in India, every state, every district has this disaster management authority. So after this earthquake, all that started working on a war footing. So you can see, again, reinforced concrete buildings failing like pack of cards. I mean, it is not expected that these buildings will behave like this. Then I'll move to different type of building here. These are not reinforced concrete buildings, but the collapse of entire cities and entire towns and villages happened in Iran in 2003. So these are photographs of the town called Bam in Iran. So the earthquake was 6.7, big earthquake, but not as big as 7.7 or 6 that we have just seen. But you can see the damage. Now these are masonry walls, URM walls, URM buildings which collapsed. Then again, reinforced concrete structures which were damaged unexpectedly. So this is 2004 Sumatra earthquake in Indonesia, huge earthquake, 9.3 magnitude. And this photograph that you are seeing here, this building is in Port Blair. Now, and this building is also in Port Blair. It's a small building, two-story building, and you can see what has happened to this building. There's nothing above this. There's just a porch. So very small structures, not expected that they will behave like this. During an earthquake which occurred almost 1100 kilometers away. So the epicenter of this earthquake, 26 December 2004 earthquake, was about 1100 kilometers away from here. So that means something happened in New Delhi and damage has occurred as far away as Hyderabad. So that's what we are talking about. Generally, it is not seen. So what has resulted into such kind of unexpected behavior? These are the questions that we'll try to address some of these questions today. Again, 2005 Kashmir earthquake, you can see a very different combination of buildings that suffered huge damages. So on the left side, this figure shows you complete destruction of unreinforced masonry buildings, old buildings, and you can see the type of informal construction here, the type of rubble that is used in the construction. Right? Any type of rubble, any type of construction technology that may not be suitable for this region, which is highly prone to earthquake, was used here. Similarly, in the same earthquake, in the urban areas, we found huge damages to the reinforced concrete structures as well. So here we can see the 4-story building completely crashed, demolished after the earthquake, collapsed. Then similar kind of construction technology and typologies are seen in China, in many cities, and similar damages also are observed. So these are reinforced concrete structures. Again, you can see 4 or 5-story buildings. These are the buildings that we have been seeing mostly, which are suffering damages. So 2008 China earthquake, again very big earthquake, 8 magnitude, where we also found that huge boulders, they slid down the hills and they damaged the buildings as well as these cars and other structures. 2010 Haiti earthquake, again combination of reinforced concrete buildings and equally the poor performance shown by the unreinforced masonry buildings. So this is the main palace of Haiti, where the president used to live, and you can see complete collapse of this palace, unreinforced masonry. No doubt that this type of construction was going to collapse because of the 7 magnitude earthquake nearby. And those of you who don't know where is Haiti, please have a look at Google Maps and you'll be surprised to see the location of Haiti. It is very, very near to the United States of America. 2010 China earthquake, similar problems. See, unreinforced masonry buildings. So these are, you can see the type of slate, type of masonry that is used, informal, huge thickness of the walls. There's no cement that is used here, all mud. And you can see the roof, again, very large thickness of the roof constructed with masonry and the mud. So these are 1 feet deep slabs sometimes. And you can see here how much is the thickness. And so such buildings have collapsed in large numbers during these earthquakes. And similarly, these are some reinforced concrete buildings, again 3-story, full story, collapsed completely. Even in countries which are developed, so like New Zealand, small country, but developed country, they spend huge amount in maintaining the structures, in construction, in design codes, everything. But then after this 2011 earthquake, which was not very large earthquake, but occurred very near to these structures, you see, this is unreinforced masonry building, a church building which collapsed, part of that building collapsed, and also some of the reinforced concrete structures. So these are, again, unreinforced masonry buildings. So not only in the developing or underdeveloped countries, but also in the developed countries, we have seen these similar types of problems. Then in Japan, Japan is of course an earthquake-prone country, but this earthquake particularly was known for the damages that it inflicted on various cities. So 2011 earthquake, magnitude was 9.0, very big earthquake. So here, not only the shaking, but also the tsunami waves resulted in huge damages. So whatever you're looking at here, most of these buildings were damaged due to tsunami, but some buildings which are standing, you can see some cracks and some damages which were due to the direct effect of earthquake shaking. Then 2011 Sikkim earthquake, 6.9, one of the biggest earthquakes in recent past that is this region has experienced, and we found large number of reinforced concrete buildings constructed on slope. They suffered huge damages. So this was a 5-story building actually, and you can see how cascading effects has resulted into complete failure. The reinforcement bars are visible here. It's very obvious why these buildings failed, and we'll discuss this later. A similar building, see from this road, this was a 2-story building, but actually it was a 5-story from if you look from behind. That is how the buildings on slopes are constructed. So most of these buildings, they suffered damages during this earthquake. Then again, Turkey earthquake, 7.2 magnitude in 2011. Large number of reinforced concrete buildings again failed. And when these buildings fail, these heavy roof, when they collapse on the below floor, this entire 2-story will collapse on this floor and so on and so forth. So it becomes very difficult to get away from these buildings at that time if there is not enough warning. You can see what has happened here, right? So tilting, when the buildings are constructed on the slopes, that has been a common feature among all these earthquakes. 2015 Nepal earthquake. You can see reinforced concrete buildings as well as the unreinforced masonry buildings. So during this earthquake, we have found that very old temples, which were very famous in Nepal, they suffered unrepairable damages. And you can see how old these buildings were. These are some of the buildings which are part of the temple complex. And you can see the thickness of these walls, huge thickness of the slabs. But unless the perpendicular walls are connected properly, we are going to see such kinds of failures. 2016 Imphal earthquake, another big earthquake, 6.7 magnitude in this region, Imphal, resulted in such failure. So reinforced concrete member. So this is a very famous women's market in Imphal, Ima Ketel. So there are 4 such markets, and out of the 4, 2 or 3 suffered some damages, 2 suffered huge damages. So all these columns in this market complex, they suffered such kind of damage. So later on, concrete jacketing was done in these columns. And such collapse of a part of the structure. So this is a church in Imphal, and you can see how a part of the structure has collapsed and penetrated through the roof. 2017 Mexico earthquake. So 2 earthquakes occurred very near to each other on 17 September and 19 September. So, I mean, people say that one is the aftershock of the other, but then both of these earthquakes were so high, so big, that you may treat them as separate earthquake, and huge damage. You can see reinforced concrete buildings completely detached from these foundations. And this again a 6-story building. You can see these slabs lying above each other. I think this was a school building or a similar community hall building. Then in Sonitpur in Assam, another 6.4 magnitude earthquake occurred in 2021. Luckily, the epicenter of this earthquake was quite deep. Hypocenter was quite deep, and the epicenter was slightly away from the habitated areas. So we did not find too many buildings collapsing here, or actually none of the buildings collapsed, but there were few buildings which tilted. There were some cases where the walls damaged out of plane, in plane. Such damages occurred, and then huge cracks in the ground, and there was a liquefaction near the Brahmaputra banks. So then in 2021, another earthquake occurred in Haiti, 7.2 magnitude. Same situation, similar earthquake, same situation. Reinforced concrete buildings, unreinforced masonry buildings, how they collapse. So now I think you can see that the places are now being repeated. So There were earthquakes in Haiti, there were earthquakes in India, there were earthquakes in Turkey, Iran, all these places, Nepal. So these are now being repeated. But the major point here is, though the earthquakes are repeatedly occurring in these regions, the important point is damages are also repeatedly occurring in the regions. We might not have learned any lesson. That's why the similar type of damages are occurring again. So this 2022 earthquake was a smaller one compared to the previous one. And you can see how unreinforced masonry buildings have suffered damages. Again, Turkey earthquake, 2023. Right? Two earthquakes occurred, 7.8 and 7.7. So that was the border of Turkey and Syria, and you can see huge damage to reinforced concrete buildings. Now, looking at these damages, what we realized that, and these are the unreinforced masonry structures, what we realized that the design was very poor, the detailing was very poor, the connection between different elements were poor, and of course, with some luck involved here, basically the amalgamation of poor engineering, the poor material, and a big earthquake nearby that resulted in such failure. 2024 Japan earthquake. So again, you can see how liquefaction, how the foundation failure resulted in such huge collapse of big structures, big buildings. These are again the reinforced concrete structures as well as the steel structures collapsing. Then the recent 2025 Myanmar earthquake, 7.7, and this is the earthquake in which we found that building in Indonesia collapsing because of this earthquake in Myanmar. So that was really surprising how a building in Indonesia could get damage and that kind of damage. But then the plate tectonics in this region is such that these waves can transfer to long distances. And again, reinforced concrete buildings that are collapsed. So what we have seen is that the RC buildings have collapsed. They have suffered huge damages during the earthquakes, past earthquakes in all these countries. Developing, underdeveloped, all these countries. Then the second type of building that have suffered huge damages are the unreinforced masonry buildings. These types of buildings, which are vernacular or the traditional building typologies, they have not suffered much damage during these earthquakes. You can see here during one of these earthquakes in Turkey, the reinforced concrete buildings suffered huge damage, but the adjacent building, which was constructed using this Himits or Baghdadi construction technology, it did not suffer the similar kind of damage. There were, of course, some damages, but then not categorized as collapse. So these damages can be repaired. Similarly, in Kashmir, there is Dhajji Diwari system, there is a Tak construction system, which did not suffer similar kind of damage. This is again similar type Himis or Baghdadi construction. So even the very good government structures, the housing, some government departments, they are housed in these constructions, but the damage was not significant to these structures. In Assam, there is a housing typology that is called Assam type house. So it is visible here. So this is a school building, small building, but this is very old building, by the way, maintained very properly. It did not suffer any damage during any of these earthquakes. This building is again Assam type housing, constructed about 120 years back, and it is still functioning as a public works department building, PWD building. So what we have seen that these vernacular housing systems or the traditionally built houses, they have not suffered significant damages during these earthquakes. But the new construction technologies, the reinforced concrete, they have suffered huge damage. Now, what is the reason? That's what we are going to discuss next. So what we have seen is that the most common building that are constructed in India is from a material from masonry. So masonry is the most common construction material in India. It comprises of more than it results in, it is used in more than 80% of the building stock in India. So in India, more than 80% of the building stock is unreinforced masonry. Now, why is it so? Because bricks are economical, they are very easily available in various shapes and sizes and texture. So almost every building has masonry. You can think of this building, which is New Bombay, Navi Mumbai, or this building, which is Gangtok, the capital city of Sikkim. One very organized construction, very organized manner, another haphazard manner, haphazard growth. So all these buildings have masonry in some form or the other. Now, use of masonry in these buildings govern how these buildings are going to behave during the earthquake. So based on the usage of this masonry in different buildings, we have considered 4 building types, and then we try to determine the reasons for their poor or their good performance during the earthquakes. Now, how did we find out these 4 building typologies? If you look at this map, here the seismic map of India, seismic zoning map of India is visible. On that, what we have done is superimposed with circles. Now, the colors of this circle, they indicate the population. So the red color circle means very highly populous. Blue color means highly populous. And then comes the yellow color and then the green color. Of course, India is populous everywhere, but even in that, we have huge concentration of population here as well as here. And then comes these regions, the blue circles and the yellow circles. Not only that, the size of the circle, it indicates the density of the unreinforced masonry buildings. So bigger the circle or the ellipse means more unreinforced masonry buildings are constructed in that area. So what we are looking for is big red circle or big blue circle or big yellow circle. So this is the region where there is a huge seismic risk, either because the population is large or because majority of the buildings are constructed using unreinforced masonry. And you can see that most of these regions, you see, they are also highly seismically prone areas. So this entire part of India, this part of the country, so this is highly seismically prone. So based on this, we came up with an idea to test 4 different types of buildings which are most popularly constructed in India. The first of these is masonry infilled RC frame building, of course, because that we have seen that these buildings suffer huge damages during earthquake. Then the next is unreinforced masonry buildings, because we have again seen that these are the buildings which suffer almost after every earthquake. We find that URM buildings suffer the most. So we have considered these. Now this building that is visible in this photograph, I'm sure some of you might recognize it. This is 120 years old unreinforced masonry building, which was constructed in Port Blair during British time as a cellular jail. So this is what they used to call Kalapani. They used to send our freedom fighters here. So this was originally a very vast structure. So you can see here, this is the central tower, watchtower, and there were 7 such wings which emanated from this central watchtower. So today, I think 3 or 4 such wings are still standing, and they attract large number of tourists. Out of 7, 3 have collapsed completely during last 120 years, but 3 or 4 are still standing. So this is a pure, completely unreinforced masonry structures. All these arches, everything is reinforced. Everything is unreinforced masonry here. But not all buildings have performed such well during past earthquakes that we have already seen. So the third type of construction that is there in many countries now is confined masonry buildings. So these come somewhere in between reinforced concrete structures and unreinforced masonry structures. So a combination of these two gives us a confined masonry building, and I'll discuss more about it later. What is the difference? Then we have selected the fourth building typology, which is a vernacular building, traditional building in this part of the country, in Guwahati, in Assam, in the northeast. In fact, this type of building is very common along the Himalayan belt. So the Assam type houses, which are also known as the Ikra houses, they are considered as these types of buildings are considered the fourth building type for this study. So here, the masonry infill walls are used below sill level, so up to this level. Below this, these are all unreinforced masonry walls. But above that, there are no masonry walls here. We'll discuss more about it when we start discussing about the tests. So then what we did, this is the first building type, reinforced concrete frame buildings. So we tested large number of such frames without infill, with infill, different types of infills, different strength of infill, different materials, somewhere flash bricks, somewhere clay bricks, all these, whatever possible at that time we tested. We also considered different areas of openings in these walls. So if I remember correctly, we tested more than 25, 30 such frames under the earthquake of lateral displacement applied here at the slab level. And we got very good insights on their behavior. So today I'm going to compare out of those 25, 30 tests, I'm just showing you results for these 3 tests. This is how the tests were conducted. So the specimen, the frame specimen was connected to the strong floor rigidly, so it did not move at the base. And the displacement loading was applied using the servo-controlled hydraulic actuator at the slab level. And the response was recorded with the help of these LVDTs, the strain gauges, and the laser displacement sensors, which are connected at different places. So you can see the reinforcement detailing, the locations of the strain gauges wherever we have used, all that is visible here. So what am I going to show you is the video of one of these tests. And the test was carried out in a slow cyclic manner because we wanted to record the damage to different members during this test. So though the test took about 2.5 hours or 3 hours to complete, but I will show you the test in very fast forward manner. Maybe about 30, 40 seconds, we'll see the entire test. So please try to see how the damage starts in these walls, the infill walls, and how that damage is then transferred to these reinforced concrete columns and to the beams. And see if there is any damage to this beam below, the foundation below. So this is the infill frame with class 1 clay bricks. You can see the load applied from the top and the displacement which is applied using this actuator is also visible here. So you can see we have already applied this displacement and the cracks have started forming in the masonry wall, which are then transferred to the columns. And you can see how cracks in the infill walls are transferred to the columns. The column starts developing cracks because of these infill walls. And depending on the location in the column, you can very easily see that this is the shear type of failure that is occurring in the columns. They are the flexural cracks, and again the shear cracks on the top. Now you can see how the column has completely failed at this displacement level. And this is the final failure for this frame. So both the bottom of both the columns Both the bottom and the top of both the columns have suffered huge damage. In fact, there's a failure, and the wall, of course, has completely gone away. But interesting point here is the wall resulted in the transferring of the damage from wall to the column. All these cracks, they started in the walls and then they transfer to the columns. So when we provide walls in the frame structure, we have to be careful about it, that the walls can also damage the columns. This is the lateral load displacement curves for the 3 frames. Here, there were no infill walls used, a bare frame. So you can see the overall strength of this bare frame was about 35 kilonewton, and the drift level with up to which it went was about 6%. Now, as soon as we inserted the infill walls, there was a tremendous increase in the lateral stiffness. Several times you can see the slope of this line and the slope of this line. Not only that, the strength also increased to about 105 kilonewton. So about increase of about 3 times in the strength and about 8 to 10 times in the stiffness. That resulted because of presence of these infill walls. And the drift capacity was about 5%, slightly more than 5%. Right? The third case where we had a window opening. So you can see stiffness is large, slightly less than this infilled, but it is still large. The strength is also much more than the bare frame, but less than the fully infilled frame. So now the strength is about 70 to 75 kilonewton. But the ultimate drift again remains almost similar, 5 to 6%, which is huge. And if you remember IS 1893, it says that the design drift should be about 0.4% only. So we are talking about 0.4%, that will be somewhere here. This is satisfying the criteria. And 0.4% is somewhere here, which is, I mean, of course, satisfying, but the ultimate drift that it has resulted in about 5 to 6%. Huge drift. Then the second type of building that we considered was unreinforced masonry. And here also we tested large number of walls and buildings. So I'm just showing you some of these results, which are very interesting. So I'll compare these 3 walls first. So without any opening, with door opening, and with window opening. So for the comparison, I'm just showing you video of one test. And again, the testing took place in a slow cyclic manner. So displacements were applied using these actuators here. And there were response recording using the laser displacement sensors. And the test will be shown in fast forward manner. So the displacement that is applied at the top is visible here. This is, I think, about 2 mm, 2.5 mm displacement is applied. Since it is very less, you are not able to see perhaps the movement of this wall, because in case of the previous frame, the reinforced concrete frame, it went up to about 100 mm, so we were able to see. So this here we have just reached about 5 mm displacement, and you can see with the movement of the people, and suddenly it failed. So about 6 to 7 mm, you can see suddenly, without giving any warning, this unreinforced masonry wall failed. And we had to stop the test on an emergency, because otherwise this will completely fall. And what we observed was not surprise, because the cracks were started forming near the door opening because of the area of huge stress concentration here. And the cracks formed at the base because of large moment demand here, both the sides, and of course from one end. So this is how the unreinforced masonry wall behaved compared to the RC frame. Now look at the load. So the full, without door opening, the lateral load was about 25 kilonewton. But the drift was only about 9 mm. So this 9 mm is about 0.3% drift, which is very less compared to the RC frame, and it does not even satisfy the IS 1893 criteria. None of these walls. So what we saw testing for this wall with door opening, and you can see it failed at about 6 mm suddenly without giving much warning. And the wall with window opening, it resulted in 12 mm displacement failure. But the strength was almost similar, 20 to 25 kilonewton. Right? So this is a major difference between a URM structure, unreinforced masonry building, and a reinforced concrete frame building. The drift capacity is very, very limited in case of unreinforced masonry buildings. Then what we did, we combined all these walls together. So these walls were individually tested before. So we combine them now. This is one wall with door opening. There is another wall here with window opening, another wall here with window opening, and this wall is a solid wall. So this is a full-scale building, unreinforced masonry, that was tested using similar test setup. So servo control hydraulic actuators, then the LVDTs, the laser displacement sensors, all were used. Now here you will find that because of the box action that was created by combining the four walls together, by joining the four walls together, you will be able to see that the building does not fail immediately when the cracks are formed, unlike the single walls. So this is the test video. Again, I'll show you it in a fast forward manner. So immediately you see this crack formed. As soon as the crack started, the crack formed. And not only this crack here at the bottom and crack here at the bottom. So this is very similar to the failure that is observed in a single wall, with the difference that it did not collapse completely, but this part of the structure was completely separated from the overall building. And it was rocking now. So this type of failure, rocking failure. So at about 15 mm, 20 mm, we found that this building failed. Again, a brittle type of failure, but because of the box action, total complete collapse did not occur. Now, the third type of building that we considered is the confined masonry building. Now, what is the difference between this and unreinforced masonry building and the reinforced concrete frame building is very interesting. First, there's a difference in the construction process. So in confined masonry, we first construct the walls and then we construct the reinforced elements. Now, these reinforced concrete elements are called the tie columns and the tie beams, which are different than the columns and the beams. The difference is the size. Size of these tie columns and tie beams is very small compared to the normal columns and beams that we see in reinforced concrete buildings. Also, the reinforcement detailing is very minimal here. In case of tie columns, there are only generally 4 bars provided, and the shear reinforcement that is provided is very less. So maybe 6 mm bars or 8 mm bars at 300 mm center to center. That's what we are talking. But in case of reinforced concrete buildings, these frame buildings, the frame, basically the columns and the beams, are designed for all the possible loads. They are constructed first. Then the walls are constructed. So that is a major difference here. In case of reinforced concrete, the reinforced concrete frames are designed to carry all possible loads. In case of confined masonry, the walls are designed to carry all possible loads. The role of tie column and tie beam is just to confine the wall. So this is the second difference, wall versus infill. The third difference is the load transfer. So basically the walls transfer the load from the slab to the bottom, but in this case, the columns transfer the load from the slab to the bottom. And of course, the structural system is different here. connection between the tie columns and the walls, what we do, we provide such kind of arrangement. Such kind of toothing is there. So this obviously improve the connection. Now, if you look at the lateral load deformation shape, or the way these buildings behave under lateral load is very interesting. In case of infill wall, we know that the diagonal strut will form and some part of the column, some part of the infill wall will be under compression, some part there will be a gap here between the frame and the infill, but it doesn't happen in case of confined masonry. This is because the wall is required to resist all the load. So this confined, the tie column and the tie beam are supposed to confine the wall and remain together forever. So that is a major difference here. So we cannot simply model the confined masonry walls as we model these walls in case of RC buildings. So the behavior is different here. So then in this case, we tested again several walls. So I'm showing you results for these three walls with aspect ratio 2.0. So you can see there's a slender wall here. In case of unreinforced masonry design, or even in case of confined masonry design, aspect ratio plays a very important role. So this was for aspect ratio 2.0, this for 1.5, and this for 1.0. And these frames, these walls were tested with similar setup. So the lateral loads were applied in the form of displacement at the top slab. And this was constructed on this beam, which was rigidly fixed to the bottom rigid floor. So let me show you this video, which again, in a fast forward manner, and try to see how damage in this masonry wall occur and how it resulted in damage to the tie columns. So you can see that the lateral displacement is applied here and how this crack starts appearing in the walls. And these X cracks are because of the cyclic action of the load. You can see the interaction crack between the tie column and the wall, the cracks transferring to the tie columns, all that is very easily visible here. And then finally, the failure of these walls here. This is how the confined masonry wall behaved. Now, it resembles the behavior of reinforced concrete frame structures. Well, but there's a difference in these two. But if we make confined masonry structures properly, they can behave just like a reinforced concrete frame building. So these are the behavior of the three specimens that we tested for AR 2.0, 1.5, and 1. And you can see the strength is reaching almost 55 kilonewton here. In case of AR 1.5, it reached 60. And in case of 1.0, AR 1.0, it reached almost 80, 85 kilonewton. So the strength-wise, the confined masonry buildings are good. But more importantly, from the drift point of view, you can see they are reaching about 4 to 5%. Ultimate drift, here they are even reaching 6%. But in case of AR1, which we have, which you can see the type of failure it occurred here, it's a shear failure. But in case of the AR 2.0, we have seen how cracks were distributed along the height of the frame. And so the behavior was much better. But here, since the cracks and the damage was limited in this region, the behavior was not very good, but still, you can see the drift was about 2.5%, and the strength was maximum here. And now finally, the fourth type of buildings that we considered. So this is the vernacular Assam type housing. We tested again all these frames and buildings and all these joints separately, the material, everything was done. Today I'm showing you these 4 frame results. So in frame 1, what we did, we removed these walls from the top. Only this unreinforced masonry wall that is there up to the sill level is considered. Here, these members are all wooden members. These are timber, which are connected to each other using very interesting connections. And there are grooves in these members, there are holes in these members in which these ICRA walls are connected. So the ICRA walls are basically the long shoots of the bamboo. So they cut this bamboo in long shoots, and then they insert these bamboo in the grooves here, as well as the horizontal shoots of the bamboo. They are inserted in the holes here. And over that, we do either the mud plaster from both the sides or the cement plaster from both the sides. So these are the walls. So in fact, there is not a real connection between the wall and the frame. These are just simply inserted there. So you can see two different sizes of these walls here. So these are called ICRA walls. In olden days, instead of bamboo, people used the river reed to construct these walls. But nowadays, since bamboo is very easily available, they use the bamboo here. So the third specimen had a window opening and the fourth specimen had a door opening. So these are the four specimens we tested. And let me show you the video for this third specimen in which there was a window opening. Now, similar test setup was there. Please concentrate on what happens to these connections. These connections here. So all these connections which are made of wood, please have a look at them. Please concentrate how this frame, single frame behave under this action. So you can see we have already reached 20 mm, 22.5 mm displacement here. But there is not a single crack in the structure except for this crack in the masonry wall at the bottom. Now, the reason why masonry wall is provided is to prevent the ingress of moisture, the stray animals in the house. Now, with about 40-45 mm displacement, I think this 140, you can see what is happening to this connection here. You can see the ICRA wall here. The bamboo shoots are visible here now. And see how this connection is actually breaking apart and then again it is joining. Now we have reached a displacement of about 230, 215 mm. See what has happened to these, all these connections breaking and then again connecting. What happened to this vertical connection between the frame structure, the wooden frame? So that was very interesting. This frame where you don't have the ICRA wall, again, it was very flexible. The stiffness was, initial stiffness was very less. The strength was also very less, only about 10 kilonewton. The drift was almost 8 to 9%, which is huge. When we add the ICRA wall here, you can see the tremendous increase in the initial stiffness as well as the strength. The strength reached almost 22, 23 kilonewton. The drift was, say, 8 to 9% again. Now, this 8 to 9% drift is almost double the drift of reinforced concrete frames and the confined masonry frames. So it is huge. And even after that 8%, 9% drift, you can see that it does not fail. And we have seen how all these connections were broken. But then in the opposite directions displacement, it again, we found that it again regained. They joined again. That is because of very flexible connections that are provided here. A very flexible connection that is between this member and the ICRA wall. All these connections were very flexible. And you can see the vertical connectivity, it simply broke by several centimeters, right? And then it again came back. When we provided the window opening, you can see the performance remains more or less similar. Not major difference, but then when we provided the door opening, then we found that the drift reduced drastically. So this is one vulnerability we observed in the historical construction methodology that they used. These frames here, they were not inserted into the foundation. So that is the recommendation that we have given to the state, that there should be a foundation for these door frame as well. Now, then what we did, we combined all these walls together and constructed a room. So this is a full scale Assam type house room, 3 meter by 3 meter by 3 meter. And we tested this entire house on a shake table. So we wanted to see how this entire house behaved during real ground motions. What I'm showing you is the test result for the staffed ground motion applied at the base on the shake table. And the peak ground acceleration that I'm showing you is 1g, which is huge. Now, this building was subjected to 112 ground motions from very low values of peak ground acceleration to very large 1g values of peak ground acceleration. There were 5 different ground motions, past earthquakes, as well as 1 simulated ground motion, and we varied the intensity. And in between, after every earthquake and before every earthquake, we also applied the white noise to record the natural frequency, to measure the natural frequency of the house. Now, the natural frequency gives us if there is any change in the behavior of the house. If there is any change, if there is any damage, the natural frequency will change. So the natural frequency will reduce basically. So in order to check that, we applied white noise also. So what I'm showing you is the last test, 112th test for this house specimen. And let me see if you, let me, please let me know if you see any damage to this house because of this very large earthquake. And this I'm showing you in real time. This is not fast forward. I hope you can see the relative motion between the base and the top. Because it's a very large ground motion, you can very easily see that relative motion. These are the accelerometers that are placed at various locations in the house. So these are the accelerometers. These are here, there were LVDTs and displacement sensors to record the displacement. And if you think that this is a small earthquake, the student who did the test tried to stand here. During the test, he couldn't stand because it was a big earthquake. He had to literally lie down. So the test is almost over. And I'm sure you might not have noticed a single crack on this house. It's a big earthquake, not a single crack. There's no doubt how these houses are behaving like the way they were being. Perfect behavior, no damage at all. But when we look closely, we found that there were some loosening in the nails. There were some minor cracks at the interface of this timber and the masonry. All that happened, but these were not visible from a distance. Now, because of these minor cracks, what we found that the natural frequency, it reduced by about 15 to 20%. But that is not a real reduction because if there are, let's say, reinforced concrete frame structures or unreinforced masonry structures, the reduction will be multiple times. So this is the way this entire building behaved during real earthquake. But the student said that unless he fail this building, this structure, his PhD will not be complete. So he was literally worrying about his PhD. He said that I have to fail this building. So then what we did, we shifted the entire house after 112 ground motions were applied on this house. We shifted that from shake table to this previous arrangement in which we can apply large lateral displacements here. So in the case of shake table, we could apply only about 10 mm or 15 mm relative displacement between the bottom and the top. So that resulted in no cracks. So here, when we can apply plus minus 250 mm displacement at the top, let's see what happens to this house. Now this test I'm showing you is in the fast forward manner because otherwise it will take a long time, 2 to 3 hours. So you can see we have reached 20 mm relative displacement between the bottom and the top and nothing, not even a crack, not even an interface crack. At 40 mm, 45 mm, I think you can see there is a gap here now. And this connection has broken at 70 mm, 75 mm. But otherwise there's nothing. Now you can see at about 90 mm, there's a connection breakage here. At about 105 mm, there's some minor damage here at the frame. Now we have reached 120 mm. And slowly you can see that the connections which are broken, they are again coming back, right? Like we have seen in case of the single frames. See, this is how the different connections, they are separated and then they are again coming back. 180 mm. Now we are reaching 200 mm and you can see the ICRA walling, the bamboo ICRA walls here that you can see the connection. 225, 230 mm. There is no sign of collapse of this house. 240 mm. Plus minus 240 mm. So we push this structure to plus 40 mm and then we brought it to 0 and then we pull it by another 240 mm. So 480 mm displacement, both plus minus that we gave. This house did not collapse. Then what? PhD has to be completed. So then we changed the arrangement, the setup, and when we said that fine, we will not apply the displacement in a cyclic manner, but we'll simply push the structure by 500 mm until it fails. So no cyclic, simply pushing. So that resulted in the failure of that specimen, but I'm not showing you that video again because it's simple. Whatever is visible here, it simply increased. So these are the testing of all 4 types of specimens that we tested. Now what we did, in order to compare the response of all these buildings, all these frames, there's no direct way of comparison, by the way. So this figure that I'm showing you, you can treat it as a cartoon, as just some way of comparing different results. So what I did, the lateral loads that we obtain in all these tests, I'm dividing them with the self-weight. So that gives me the base shear ratio. And this base shear ratio I'm plotting with respect to the drift that these specimens were subjected to. So this is a normalized response that you will see in this figure. And all these frames and the different buildings that we just saw, I'm going to compare here now. So the first building that we tested was unreinforced masonry building, solid. And you can see the behavior here. So if you remember, this was about 20 kilonewton, but when I divide with the self-weight, it's only about 0.5 here. So this is where the unreinforced masonry building is. If I want to see what happens with the door, more or less the overlapping behavior with lesser drift, and drift, of course, is very less, 0.3%. The third specimen with the window opening behaves slightly marginally better because of the grill. So that grill was sorry, not the grill, but because of the lintel band. Lintel, not the band, only the lintel. So this is where our unreinforced masonry buildings are. Now the next that we tested was a confined masonry building. So this is the confined masonry. And you can see tremendous improvement in the strength, but we are not bothered about the strength much, but the very large increase in the lateral drift, 4%. This is where we have to think like how and why these buildings performed well compared to the unreinforced masonry buildings. Obviously, because they can sustain huge amount of drift. That is the reason that these buildings performed well. The second type of confined masonry with aspect ratio 1.5. You can see similar strength and the drift further increased. The third frame with aspect ratio 1.0. And this with aspect ratio 1.0, because there was a shear failure, the drift is less, but it is still reaching about 2%. Right? And the strength did not reduce. Strength is actually highest among the 3. So now you compare the difference between confined masonry and unreinforced masonry. Simply by providing these small elements, which are tie columns and tie beams, we can improve the performance tremendously. And it has been observed during previous earthquakes that these confined masonry buildings have not suffered much damage during the earthquakes. Assam type house, and you can see that these buildings can go infinitely as far as the drift are concerned. You see the strength is not much here, but then the drift is reaching almost 8-9%, highest, right? And compared to all other structural systems, the stiffness is very low here. These are very, very flexible structures. The second type where we provided the infill, ikra wall, and the third type where there were window opening and the door opening. So you see that stark difference, a remarkable difference in the behavior of these three building typologies: unreinforced masonry, the confined masonry, and the Assam type housing. Now comes the reinforced concrete frame buildings. This is the bare frame. There's no comparison. Like bare frame is behaving much, much better than any of these frames. Large strength, high deformability, very good drift. When I insert the infill wall, you see the behavior here. There's no comparison between these buildings, the unreinforced masonry versus these buildings. Look at the increase in the strength, the stiffness with remarkably high lateral drift. This is the infill frame with 10% opening. So these are the buildings that we tested, and I mean, not all, but some of them, and I'm just showing you the comparison. Now there's no surprise why the unreinforced masonry buildings behaved such poorly during past earthquakes. But there's a surprise why these buildings, which are otherwise very, very, which showed very remarkable performance as far as strength and drift is concerned, why these buildings should suffer such poorly, such behavior. It is surprising. So the only reason of explaining that is they are not designed properly or they are not constructed properly. These are the two reasons. Either the materials are poor or the engineering is poor or the workmanship is poor. Only because of that, these buildings are behaving very badly. Confined masonry buildings and Assam type house, you see, Assam type house will not fail. Confined masonry buildings, much better performance, even with respect to these. Because they are not, the RC elements are not designed here. The masonry is designed. So with this, I really found no surprises. We have to improve the construction practice. We have to use good materials and follow design codes. With these 3 points, I'm sure the best buildings that we just saw in the previous figure, the reinforced concrete buildings, will remain best after the earthquakes. Otherwise, there will be catastrophic failure of these buildings. Now, in our semi-urban areas, in villages, I understand that there are limited structural engineers. There are guidelines are not there. The codes are not there. So in such cases, why not to construct the confined masonry building instead of reinforced concrete buildings, which cannot be designed or constructed without the help of engineers, right? But then the confined masonry buildings can be constructed. And if we do that, the performance will be much better. The seismic risk will come down. If I ask you, out of these 4 typologies, which one would you adopt? The answer will be very difficult. Given a chance, everybody would like to adopt the best building, which is reinforced concrete. But then adopting is something else. Designing them properly is something else. We have to design them. We have to construct them, use good materials. Only then they will behave perfectly. Now, another point that we saw was masonry can save the structure, but only when it is used properly. But it can damage the structure severely if we are not using it properly. We have seen how masonry can inflict the damage on the reinforced concrete frame members. And obviously, it is time to embrace our traditional and vernacular housing systems because in villages or in semi-urban areas or even in urban areas, if you have enough space, there's no reason to construct reinforced concrete building. I mean, the traditional Assam type housing, they have performed really well during all these past earthquakes. So that is all from my side. Thank you very much for listening to this entire presentation. And let me thank my students who have done these studies. My simple job was to just present before you. Syed Humayun Basha, who did the reinforced concrete work. Thanks to Umang Chaudhary did the unreinforced masonry. Biswajit did the Assam type housing, and Bunisha did the confined masonry buildings. And I also thank the Department of Science and Technology for supporting all these studies. Thank you very much.
Thank you, sir. Thank you so much for providing that comprehensive overview on earthquakes and then damages during such events and the earthquake affected buildings along with their possible failure reasons. And I'm sincerely thankful to you for taking your precious time to deliver such an insightful and engaging presentation where you have covered most of the aspects along with the risk mitigation strategies. Your talk was truly valuable and much appreciated. And I'll request Akshay to continue the proceedings.
Thank you, sir, for that insightful and inspiring session. Now we will take the questions from the participants.
Sir, we have a few questions. If you allow, I will read one by one. Yeah, okay. So the first question is, from your field observations, which structural deficiencies have been the most consistently linked to the severe earthquake damages in India?
If you consider the reinforced concrete buildings, then poor detailing.
Okay.
That results in most of these damages. And if you consider the unreinforced masonry buildings, then the poor connection between different walls.
Okay.
So these are the, yeah.
So you mean to say the wall-to-wall connections along with the wall-to-floor
Yes.
connections?
Yes, yes.
The second question is, Mr. Suresh Rao is asking, this 1G acceleration, which you have discussed in the slide, what it transformed to what value on the Richter scale in the real-time earthquake scenario? 1G.
See, these two are different things. The magnitude versus the peak ground acceleration are two different things. See, we measure the peak ground acceleration at a particular location, which may be far away from the earthquake epicenter. So peak ground acceleration changes as you move away from the earthquake epicenter. The assumption was that wherever the earthquake, this Taft, for example, the Taft ground motion that we used, wherever that earthquake was, the peak ground acceleration of 1G occurred at the base of this structure. That was the assumption. But it is, I mean, not the way we think of PGA versus the ground motions, right? These are two different things.
Thank you, sir. The next question is, especially in regions with high seismic hazard and informal construction, especially as far as the non-engineered buildings are concerned, like masonry, what low-cost interventions have proven the most effective, according to you?
Yes, so very good question. In fact, what we have seen after every earthquake, we see that some buildings don't collapse. There are some buildings which do not suffer much damage. And the reasons are simple. Either these buildings were constructed nicely, following the guidelines, good material, good engineering, or there are some interventions at relevant time. So there are many instances where small intervention strategies like use of the bands, seismic bands at different levels in unreinforced masonry building, they saved the building. In case of older construction where the bands were not provided during the construction, the bands in some buildings, the bands were provided after the construction. So these were steel bands. There are some steel bracings that are inserted. There are the entire loads are transferred to an externally placed steel bracing, steel frame arrangement. So many things are done in different places of the world to save these structures.
So the next question is, will the opening in the walls for windows and doors reduces the stiffness? If the answer is yes, then how it can be accounted when designing the structure in the real scenario?
Yes, of course, you consider a building in which there are infill walls in all the floors, including the ground floor.
Yes.
Then if you provide a window opening or a door opening, let's concentrate only on window opening, because it is a small opening. Door is anywhere a big opening, it will affect. In case of fully infill frame building, if there are window openings in all the infill walls, then obviously it will result in change of the behavior, reduction in the stiffness, all that will happen.
Right.
Now, we should not fool ourselves by assuming that because there is a reduction in the stiffness, let's change the design of RC members, because that is very, very tricky. We have seen that the walls can inflict damage on the RC frame. Right? So when we have the infill walls in RC frames, we have to be more careful, because the moments and the shear demand on these columns will reduce because of presence of the masonry infill. But we can't design the RC members for reduced shear and moment demand, because the masonry infill wall will fail. This is a brittle member. It will fail after a few cycles. And after that, the entire load will transfer to the beams and columns. So though there is a reduction in the stiffness, obviously, when you have the windows and the door openings, but we have to be careful not to consider that in the design for the RC members. Now, a second possibility is you have an open ground story building, right? Now you have the window openings in the walls in upper floors. Now that does not reduce the stiffness of the building, though the mass of the building changes there, but the stiffness of the building does not change much, because the ground floor, because of absence of the infill walls, is already very, very flexible. The stiffness is already reduced multiple times, and that we have seen, right? The bare frame versus the fully infill frame. So this is another reason that why should we not change the design because of presence of the window openings in infill frames.
Thank you. So the next question is related to the Assam type house. The experiment which you have shown us, it has a lighter roof, seems to be a TMT steel sheets. Will these houses show same behavior, especially the higher drift percentage, if the roofs were heavy, like in case of Tak or Dhaji Diwari system?
Tak or Dhaji Diwari are purely masonry houses, and we can construct heavy roof there because the thickness of these walls are 600 mm, 500 mm, even 1 meter in some cases. But in case of Assam type housing, historically, we don't construct heavy roof. And the reason is very simple. Here, the environmental condition, the weather condition is such that because of heavy rainfall, these roof must be slanting roof. So they don't have, they don't have a normal reinforced concrete roof where water can accumulate. That is not done. And that is why you will find the thickness of these walls, ICRA wall, is not even 100 mm. The thickness of this ICRA wall is only 45 to 50 mm. And then comes the timber posts, which depending on the height of the building, so for a single story, it may be 125 mm by 125 mm. For 2-story, usually about 170, 180 mm. That is the only thickness. So heavy roof is not a possibility here.
Okay. Thank you, sir. The next question is, it is related to the confined masonry building. What is the ideal number of stories for confined masonry structures? first part. The second part of the question is how better the RCC framed structures when they are compared to confined masonry construction.
So the number of stories or the height of confined masonry depends on the quality of the bricks that we have. In India, unfortunately, we don't have very good quality of the bricks available. So I can say that if you have 15 MPa bricks, 20 MPa bricks, individual bricks, then you can safely go for 3-story buildings. And this has already been done in India. In IIT Gandhinagar campus, we have large number of hostel buildings, the residential apartment buildings constructed using the confined masonry technology. So 3-story is fine. But in other countries where you have bricks of 100 MPa, 120 MPa, those high quality bricks are available. So you have even 6-story, 7-story buildings constructed using confined masonry. Now the second part, how better the reinforced concrete buildings are, of course, if you make them better, they will be better. If you design them better, they will behave in a much better way because of the ductility. If we are providing proper detailing in these reinforced concrete frame buildings, and the reinforcement bars are proper, the material is proper, the shear reinforcement is proper, the confinement is proper, then of course. The reinforced concrete buildings will perform the best among all these.
So the next question is, what is concrete jacketing, and will this type of intervention is done only to the structural members?
Yeah, jacketing means not really only concrete, but we also sometimes use steel jacketing. So jacketing means enclosing the damaged member in an external or additional member so that the overall capacity can be improved. Now, if it is a concrete jacketing, well, it depends when we can provide concrete jacketing or steel jacketing, but in both the cases, the performance improves multiple times. Right? So the idea is to retrofit the building. And there are a variety of methods using which we can do that. Jacketing is just one method in which we use to connect the additional members with the existing members. So some part of removal of concrete, some part of welding to the existing bars, and all that is required here. Can it be done only to the structural members? I am not sure what is the meaning there. Of course,
it means the members. The question seems like whatever retrofitting intervention we are doing, is it only to the load carrying members or also to the non-structural members as well?
Generally, we don't retrofit the non-structural members.
Structural members as such.
Yeah, the way we retrofit the structural members. For non-structural members, mostly what we do, we try to prevent the collapse. We try to prevent their high drift or high deflections in them. That's what we generally try to do.
Okay. Okay, sir. The next question is, what role can local building codes play in reducing the seismic risk given the varying enforcement levels across India?
Yeah, if it is enforced properly and if people start using these codes, obviously the risk will reduce, the performance will improve. The main problem is the enforcement. Though, I mean, everybody knows that we have to use, specifically in the earthquake prone areas, we have to use these codes. But we have seen that not many people use these codes. And that is the reason, not only in India, but also in the other countries.
Across the world.
Right? Across the world.
Okay, sir. The next question is, are there any particular lessons from global seismic regions that India has yet to adopt effectively?
Well, there are many, because many things, every day new things are coming up, and I would rather ask a question, is there anything that the world has to adopt from India?
Right.
Of course. I mean, our systems are different than the world system. In fact, when we did this study on Assam type housing, and when we published this paper, it was the most downloadable article on AC.
EAC.
And uh, none of these download happen in India. These are all from other countries. So, I mean, this, Lena Dena of research, of
Right,
all these
sure.
techniques, the engineering is continuous process. We learn from them, they learn from us.
Sir, there are two back-to-back questions on this. One is on Assam type housing. What type of wood was used to build the frame of Assam type house?
There are two types of woods. One is used, one which is a good quality timber. They call it here sal wood.
Sal
It is used sal wood. It is used for the main post that transfer the load from the top to the foundation.
Okay.
Yes. And then for the intermediate members, an inferior wood, slightly inferior wood can be used. For in this case, we used the jam wood, locally known as jam.
The next question is, why this timber braced or timber laced masonry have shown such a remarkable survival in the past Indian earthquakes? And still they are standing since last 100 to 150 years, especially in the Himalayan region belt. Most of the stone masonry buildings along with timber lacings.
Yes, not only diagonal. I mean, even if you provide vertical bracings or the horizontal bracings or wooden elements anywhere in the wall, the Daji Diwari system, the Taj system, what we have seen that the behavior is much improved. Now, why? The reason is simple, that as I told you, the aspect ratio plays a very important role. The slenderness plays a very important role as far as the masonry is concerned. So our role is always to limit the slenderness, is to limit the aspect ratio. Now, in order to reduce the slenderness, what you can do is to provide an additional wooden element in between, vertical, horizontal, and this slenderness can be along the height, the slenderness can be along the length. So all these houses, you will find that they have reduced the free length of the wall. They have reduced the free height of the wall. And they have connected to two corners with these diagonal bracings, because they have seen that earthquakes are horizontal in nature. And when these struck, how the cracks are formed. You see that the diagonal cracks, X cracks. So they knew that something is happening diagonally. So they provided the horizontal bracing, the diagonal bracing. So ultimately, what they have tried to do is to reduce this free length, free height of these walls. And confined masonry systems also does that. Yeah, we reduce the free length height.
Thank you, sir. The next question is, one of the participants wants to know what is out of plane failure and in plane failure in masonry walls. And the second question is the role of diaphragm action in masonry structures.
Yeah, so as the name suggests, when you have a wall which is acting under in-plane action of horizontal load, the type of failure is different in nature. So you'll have diagonal cracks, you may have horizontal cracks in a particular course, or the entire wall may shift. So depending on what is the least strength, either it is controlled by the joint strength, or it is controlled by the brick strength, or it is controlled by the shear strength. All the minimum strength of this will govern which type of failure mode is occurring in plane failure. So that is the in plane, when you have a wall and you have that failure. But for the out of plane loading, what happens when the earthquake occurs in the perpendicular direction? Earthquake can occur in any direction, by the way. So for the perpendicular direction, sometimes what happens when the wall gets damaged in plane, then its strength reduces automatically. And for the out of plane loading, it falls easily. That becomes very easy, right? If you don't have proper connections between the walls in different direction, so this wall will become vulnerable for the out of plane failure. So this is the wall in plane, and when it fails, In the out of plane direction, that is called the out of plane building.
And the role of diaphragm action in masonry buildings.
Yes, so diaphragm plays a very important role. In fact, when you have a stiff diaphragm, so somebody asked, can we construct heavy slabs or roof on these walls? So in unreinforced masonry, if you are constructing lightweight roof, let's say timber roof on these walls, then the performance of these unreinforced masonry buildings will be much, much poorer. Because when we are not connecting these four walls at the top,
yes,
then these four walls will start acting alone.
independent.
But independently, but when we have a reinforced concrete roof at the top that is connecting all four walls, and this is a rigid floor diaphragm, that gives rise to an action called a box action. So these four walls, they start acting together. So the diaphragm has a very important role here, especially in unreinforced masonry building and the reinforced concrete buildings.
Okay, sir. Thank you. Last few questions, sir, and then we'll wrap it up. What measures can be taken to bridge the gap between the laboratory research and on-site construction practices in general?
So that gap is taken care of by the design codes.
Design.
Yeah, so whatever we do in lab, it gets into the design code. Some of that, not all, but some of that goes into the design codes, and from the design codes to guidelines to on-site. That's how we do it.
So the next question is, which structural features make a building safer during an earthquake?
Well, there are many, and if you miss one, earthquake will find out which one you missed. Right?
True, true.
You have to solve all these.
And looking ahead, which emerging technologies or materials do you think show the most promise for improving the earthquake resilience in India?
The basic construction, if you see in India, is reinforced concrete, unreinforced masonry, but now slowly this confined masonry is coming, and then the steel structures are now coming up. Now, steel structures, again, if constructed properly, they're fast construction. If we construct them properly, their performance will be much, much better than the reinforced concrete also. Then the basic construction technology is not, we don't find many new technologies for the regular structures, but for mass construction, for example, if you want to construct some shelters immediately, very fast, then we have many technologies. Immediate construction, very fast construction, prefabricated structure. These are coming up using different materials. But for normal residential, normal structures, more or less, we have settled down to these RC buildings, to URM buildings, confined masonry, all these. There's a huge improvement in our understanding on the retrofitting strategies, the strengthening methods, the material that is used for the retrofitting and strengthening. There, we are now coming up with many, many new strategies and the materials.
So the last question of the day, it's basically an observation. We say that despite the extensive use of modern construction materials such as concrete and steel, masonry as a material has been sidelined over several decades. But when we see from the statistical point of view, you mentioned that 80% of existing housing stock in the country contributes to masonry structure. Do you think the statement is correct? Masonry has been sidelined for several decades?
Sideline, I don't remember I said the word sideline.
No, you didn't say that, but
yeah,
people has a perception.
Yeah, sidelined as far as their design is concerned. Sidelined as far as their structural use is concerned. So what we think is that this is a non-structural material or non-structural member that will not affect the behavior of the structure. That is not correct. Masonry is, of course, most widely used construction material across the world. In India, it is 80-85%. Some places it is more than 90%. But we don't teach masonry. There are very few colleges in India which teach masonry design, though our majority of the structures are masonry. But I'll not blame them, because this is the era of fashion. This is the era where unless you tell very fancy words that I'm doing this, people will not give you jobs. Right? If you tell that I'm designing masonry, so people say, who designs masonry nowadays? These are the questions that some of my students face when they appear in the interview. But I'm sure slowly the understanding is changing. I mean, people are now realizing that there's a peak as far as the design for RC, steel, all these concepts. But the failure is in this URM. The failure is poorly designed RC buildings. So the perception is now changing, and people are now appreciating the masonry can be a good material for earthquake safety also.
Thank you so much, sir. I think we have covered all the questions, and thank you for clarifying all the doubts of our participants. Akshay, it's over to you.
Oh, you
Yeah,
did not
please, sir.
ask me one question, but
Yeah,
somebody,
please, sir.
and I really like the question, so let me answer.
Yeah, sure, sir.
Why
Please.
is it necessary to fail a building to complete PhD?
Yeah. I
Yeah.
missed it. Sorry.
It is not necessary, and I never insisted the student that your PhD will not be completed unless you fail this building. I never said that. It was the wish of the student. He said,
Yes.
my PhD will not be complete. So you take it in a different
Yeah.
taste.
He wanted to test till the failure. Yeah.
Yes.
Thank you. Akshay, it's over to you.
Thank you, sir. I believe the queries from all the participants have been addressed. Now I'd like to invite Mr. Shantanu Devale to deliver the vote of thanks.
Greetings to all. I am Shantanu Devale, pursuing MTech in Computer-Aided Structural Engineering at Earthquake Engineering Research Center. It's my honor and privilege to deliver the vote of thanks on behalf of the entire Executive Committee of IIStructE IIIT Hyderabad Student Chapter. First and foremost, I extend our deepest gratitude to our esteemed guest speaker, Dr. Hemant Kaushik, for his insightful presentation and enlightening session on lessons learned, risk mitigation, strategies for the future. Today's webinar has highlighted various earthquake effects occurred in the recent past, performance assessment for various structures, damage to various buildings types during the past earthquakes, also the field observations to the recent experimental studies at IIT Guwahati aiming to improve the structural performance. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to the IT team for ensuring seamless technical support and to the design team for their creative inputs and logistical assistance. I thank our program coordinator, Dr. Sunita Paliseri, for her continuous encouragement. I also want to thank my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced the discussions and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of entire team whose collaborative effort has made this event a success. In conclusion, I extend my heartfelt thanks to each one of you for your participation and engagement. We are extremely grateful and look forward to your continuous support in the future initiatives. Thank you so much.
You're muted, Ravi.
I said thank you so much, sir, for joining.
Yeah.
Thanks a lot.
Thank you, everyone. Thank you so much.
Okay, sir.
Yeah. Bye-bye.
Mr. Sai, you can stop the recording part. Thanks a lot.